Let's think about how our equilibrium constant expression changes when we change our chemical reactions. So when a reaction is written in the reverse direction, it's written backwards, the equilibrium constant is inverted. So it's 1 over the original equilibrium constant. So let's think about that. If we look at our law of mass action, when we always do products divided by reactants. So in our forward direction, it would be the concentration of C times D over A times B, again raised to the coefficients. But if we look at the reaction in the reverse direction, now our reactants become products and our products become reactants, essentially inverting our equilibrium constant expression in the backward direction. So if we reverse the reaction, our constant, in order to calculate the new equilibrium constant, we can take 1 over 1 divided by the original equilibrium constant in the forward direction. If we change the chemical reaction by multiplying it by a factor, then our equilibrium constant expression becomes raised to that factor. So let's think about that a little bit closer. If we have our original equilibrium constant expression based on our reaction, remember we're raising each of our concentrations to the coefficients. So if we multiply the entire chemical reaction, in our example, we're multiplying by 2. That means that our new equilibrium constant expression is going to be 2 times our original coefficient. So essentially, we're raising the entire equilibrium constant expression to whatever our multiplication factor is. So it's going to be our original equilibrium constant raised to the multiplication factor. So in this case, in our generic case, it would be N. Let's look at an example where we have to add 2 chemical reactions together to get a new overall chemical reaction. In this case, we are going to multiply our equilibrium constants together to get the new equilibrium constant. Let's look at this a little bit more in depth. So we have an example where we have reactant A yielding B, and then B continues on to C. If we write our equilibrium constant expressions, products over reactants, so we would have our equilibrium constant for the first reaction and our equilibrium constant for the second, products over reactants in both cases. When we make our new equilibrium constant expression, making A going to C, we're going to multiply these together. The B's are going to cancel out, and we're going to end up with product C over reactant A. And so by multiplying our original equilibrium constant expressions, we end up with our new equilibrium constant expression. So K1 times K2. Here's an example that we can look at. We're going to start with our original equilibrium expression for taking nitrogen and hydrogen and forming ammonia. And our goal is to find the new equilibrium constant when we reverse the reaction, but also divide by 2, or we can think about it as multiplying by 1/2. So if we reverse the reaction, we have to find the new equilibrium constant. We have to take 1 over the original. And if we multiply by 1/2, for our chemical reaction. That changes our coefficients. Which means that in our equilibrium constant expression, K prime meaning the new one, which is what the notation we were given, we have to multiply our expression by the same coefficient, or raise it to the power of the same coefficient, which is 1/2. Okay. So our new equilibrium constant is going to be 5.2 times 10 to the -5th. And again, because the units get very complicated, we're writing our equilibrium constants with no units. Here's a practice for you to try. Pause the video to see if you can calculate the equilibrium constant for this problem. We first need to start by finding the equilibrium constant for the reaction of A to 2B. So our equilibrium constant expression is going to be products over reactants, so B, and because the coefficient is 2, we have to square it over the concentration of A. We're given concentrations in the problem, so we can plug those into this expression. So for reaction 1, we get 1.6 times 10 to the 4th, which means that the products are favored in this reaction. If we look at our second reaction, 2B, giving us the product Z. Again, we have to calculate our equilibrium constant. It's going to be the concentration of Z divided by B squared. So we can plug in those concentrations that were given in the problem. And we can find our equilibrium constant for this chemical reaction, 2B to Z, is 0.125. So this is less than 1, which means that our reactants are favored. So now, if we want to find Z to A, it is going to be done by first reversing our reactions. So we can go from Z to 2B. So that is the reverse of our reaction up here, which means that our new equilibrium constant is going to be 1 divided by our original. We can take 2B and form A, and again this is a reverse reaction, so it's going to be 1 over our original equilibrium constant. And then if we want to find Z to A, we are going to have to add these reactions together. So in that case, to find our new equilibrium constant, we need to multiply the two constants. So for Z to A, we would have 5 times 10 to the negative 4th. Now, if we think about this, this is smaller than 1, which means that the reactants are going to be favored.